Hello and welcome to Today I Learned Climate, the show where you learn about climate change from real scientists and experts. I'm Laur Hesse Fisher from the MIT Environmental Solutions Initiative, and today's guest is joining from a long way away from us.
I'm James Renwick. I'm a professor of physical geography at Victoria University of Wellington in New Zealand.
Professor Renwick is a lead author for the worldwide body of scientists who create the United Nations climate change reports. It's called the Intergovernmental Panel on Climate Change, or IPCC. Because these reports pull together all of the world's research on climate change, they're the best information the world has on how climate change is unfolding.
So I'm involved in a chapter on the water cycle and how that's changing. So that involves everything from, rainfall to glaciers, groundwater, lakes, anything to do with water around the globe.
We invited Professor Renwick on the show today because we're talking about water. If you've only heard one thing about climate change, it might be that sea levels are rising, and many of the Earth's islands and coastlines are at risk. But why? We're going to take 2 episodes to discuss sea level rise. Today, we're going to dig into the science, what we know and how we know it. And then in the next episode, we'll talk about what sea level rise looks like, what it means for us, and what we can do about it. Okay, so let's get started. How do we know that the oceans are higher now than they used to be? And how do we know this is because of climate change? New and old technology help scientists understand what's happening.
Basically, using GPS, differential GPS, you can look down from your satellite and tell very precisely how far away the sea surface is, down to the millimetre scale. It's pretty cool science, actually. I mean, it's the same GPS that's on everyone's phone and everything. It's done more precisely, but it's the same technology put to a really cool use. So we have these nice satellite records for the last 30 years, and we know they're reliable and precise and so on. But of course, for a climate study, you want more than 30 years of information. It's just not long enough to get a sense of any trends.
Luckily, people have been interested in sea levels for much longer than 30 years, because merchants and fishing ships have always needed to know when the tides were high enough for their ships to move safely through the ports. Port officials kept logs of how high the tide was from day to day.
We have reliable sea level measurements from tide gauges at ports around the world that go back to the late 19th century, so about 150 years of record or so. Turns out there's enough of these things around the globe that you can form an estimate of how the average sea level is changing, if it's changing. And of course, it wasn't changing for a long time until the greenhouse gas increase really started getting going.
Yeah, what we see from the tide gauges and the satellite data is that globally, on average, the oceans have been rising over the past 100 years. And in this century, the 2000s, it's been rising faster. But why? Well, it's because the Earth is getting warmer. When we burn coal, oil, and gas, we release a kind of pollution that hangs out in the atmosphere. And this pollution acts like a blanket, trapping in heat. When there's too much of it, it warms up our air, our land, and our oceans. In fact, most of this trapped heat goes into our oceans.
About 90% of the total heating from increased greenhouse gases in the atmosphere is going into ocean water. So the ocean's warming, and if you heat water, it is going to expand. This would work. You can try that out. If you put a cup of cold water in a microwave and heat it up, there'll be less room in the cup at the end of your little experiment.
In our educator guide for this episode, we give you another easy demonstration of this that anyone can do at home. To check it out, go to tilclimate.mit.edu. Of course, when ocean water expands, the only place it has to go is up. So that's one cause of sea level rise.
But the other thing that's going on has kind of taken over, and that's the melting of ice off of glaciers all around the world and from the big ice sheets in Greenland and the Antarctic. So it's making the ocean deeper all around the world. I mean, The oceans are pretty big, so you need to melt a lot of ice to really noticeably raise sea levels. And the number is one I carry around in my head. If you melt 360 billion tonnes of ice and spread that water out over the global oceans, which happen to be about 360 million square kilometres in area, you get a layer that's 1 millimetre thick. And in the global average, we've had, I think, about 25 centimetres, which is, a little less than a foot of sea level rise since the late 19th century. So that's, when you work it out, that's a lot of ice. It's trillions of tonnes of ice that have already melted off the ice sheets of the world.
So because of all the water warming and expanding and all of this ice melting, there's already been, as Professor Renwick just said, about 25 centimeters, which is about 9 inches, of sea level rise, on average, around the world. I say on average because the sea actually rises faster in some places than in others. There are a few reasons for that. A big one is how the Earth's crust shifts and adjusts as ice melts, like from the last ice age 15,000 years ago. But that's not all.
This ice on the ice sheets in Antarctica and Greenland, it's such a big mass, it basically they have their own gravitational field. They pull water towards them.
Yeah, so this ice is so massive that it pulls ocean water towards it. And when these ice sheets get smaller, it changes the gravitational pull.
When ice melts off Antarctica, a lot of that water ends up flowing into the northern hemisphere and, in fact, pooling up along the US coast. So that eastern seaboard of the US, of North America, is one of the parts of the world where sea levels are going up faster than the global average.
Around New York City and Miami, sea level has risen about a foot over the 1900s. And in certain coastal communities of North Carolina and Virginia, it's already risen by about 1.5 feet. And this is still happening. The seas are still rising. In fact, they're rising faster now than they were even a few decades ago. But because human activity is driving this sea level rise, we actually can slow it down.
If we turn off the emissions, the sooner we do that, the sooner the rate of sea level rise starts to decrease and plateau out. But we're not so sure about how long it would take to completely stop. The estimates are that maybe sea levels would keep rising for another century or two. It's most likely we would see something like a couple of feet of sea level rise, but we could see double that much over time.
And that's if we stop our CO2 emissions. If we don't, there's a possibility of getting way more than a couple of feet. To spell out this scenario, Professor Renwick takes us back to Antarctica and all the ice that it holds.
If you look down a map of the southern hemisphere looking down on the pole, there's a big continent right over the pole. That's Antarctica, the coldest place it could be. So the ice is about 4,000 metres thick on the East Antarctic ice sheet.
That's 2.5 miles of ice. And under all that ice is land. Yeah, that's why Antarctica is a continent, because there's actually land there. And all of this ice is heavy enough to push the land down.
In places, the Antarctic continent is, hundreds of feet below sea level. And it's ocean water that's lapping around the edge of these ice shelves. That's what's melting the Antarctic ice. So if this warming water around the coast can kind of get under the edge of the ice shelf and basically get over the coastline, it'll flow downhill with gravity and flow under the ice and start to float huge pieces of ice melting from the bottom up. That would really accelerate the melting of the ice and the flow of that ice out into the ocean, which is, big news, bad news. The estimates we have from modelling are that if global warming gets to be more than 2 degrees centigrade, let's say 4 Fahrenheit, then the ocean water around Antarctica will have got warm enough to cause that process to become unstoppable. And we'll lock in 4 or 5 metres of sea level rise at least. What's that? 15 feet. That would be catastrophic for pretty much every coastal city in the world that you can think of, I'd say. So there's a real, we're on a bit of a knife edge with sea level rise at the moment.
So what's the time frame that we're talking about here?
So how long would it take to melt all this ice on the West Antarctic? It takes a long time. We might lock in that melting within 30 years or so if we don't reduce emissions of greenhouse gases pretty quickly. But it would take several hundred years for all the ice to melt, and maybe even 1,000 years. So it's not something that's just going to happen over a weekend or something. We're not going to wake up and find, wow, sea levels are now, this much higher. I'm now floating. My house has disappeared. I think it's really worrying if we know that we have consigned future generations to many, many metres of sea level rise. We would be saying that all future generations would have a different map of the world. Humanity would have the time to adjust, but in the process, millions and millions of people would be displaced.
This is a lot to think about, and it can also sound very far away, a century or two of rising seas. Which is why in our next episode, we're going to bring Professor Renwick back to help us understand how sea level rise is impacting people now and what's in store in the next couple of decades. In the meantime, we'd love to hear from you. You can find us on Twitter at TILClimate or send us an email at tilclimate@mit.edu. And you and your friends can subscribe to TIL Climate on Apple, Spotify, or wherever you get your podcasts. Thanks to Professor Renwick for joining us, and thank you for listening.